messenger events, in particular gravitational waves. So thank you, Elisabetta.
Okay. Thank you, Ulysses. Welcome again. I hope you enjoyed your lunch. So, as you probably noticed from my first lecture today, I'm basically a gamma ray physicist, but over the past 10 years, I had to myself study a little bit more about gravitational waves. So I will try to give you an overview of the gravitational wave phenomenon. Also because these are some information that I think are important to really understand the challenge behind detecting gravitational waves. So this morning someone asked me why it took so long to see very high energy gamma rays. So the technological advancement and everything that was necessary to catch finally the very high energy emission of gamma ray bursts. And I would like you to feel, if you are on, maybe if you don't know, if it's something completely new for you, how hard it was to finally catch gravitational waves. Because when I first started in this, so to say, in this topic, it was not really clear to me. So it was like, okay, they detect a gravitational wave. Who cares? But it's really, it's really tough. It's really a tough history. And again, I will do a little bit of a historical journey, trying to cross the gravitational wave information with what is my expertise, so with gamma ray information. I'm not a gravitational wave person, so I am not a member of LIGO or Virgo. I have a few colleagues of mine that are in Italy that are Virgo members, but as you probably know, it's just one, let's say, very big collaboration, LIGO, Virgo, CAGRA collaboration. So, okay, let's start with the beginning. Okay, so this is probably most of you probably got some general relativity course at the university, but I will try to go, let's say, as fast as possible through this. So gravitational waves were proposed at the beginning of the century, basically by Poincaré, les ondes gravifiques. They should be emanated from massive bodies, and the idea from the beginning was that they would be propagate at the speed of light. So obviously there is a huge framework that is necessary to start to describe a gravitational wave. I will keep it at the very minimum. I hope that most of you had some previous lectures in general relativity, so probably what you will see on the slides will be at least a little bit familiar. I will put also some, let's say, functions and some formulas. Again, there is a lot of text, but if you have the slides, then you can have some more time to go through them and read them carefully. So, Einstein himself derived 3 types of propagating solution for the field equation, which we will see in a second: longitudinal, transverse, longitudinal. So, but there was a lot of doubt also already at the beginning. So, basically, the approximations were somehow misleading the community, and many were putting into doubt, so to say, the result. And the community was at the beginning not really convinced about it. So one famous paper that we need to mention, I hope everything is okay, that we need to mention is this paper by Einstein and Rosen in 1936 that was submitted to the physical review letters. I am telling you this because then I will tell you another story after 100 years about the physical review letters, so keep in mind. And the title was, Are there any gravitational waves? So basically in this paper, Einstein was saying that the answer to his own question was, they do not exist. So he published saying, no, they do not exist in the end. But actually there was a referee, Robertson, that was somehow questioning the conclusion of the paper, so it should really be there. And so Einstein was very angry with this refereeing of this paper, and he withdrew the paper. He said he would never publish anymore in the physical review letters. But then actually, thinking about this, he was convinced by the criticism of this paper, and he rewrote the paper with the opposite conclusion. So actually, that the gravitational waves actually they exist. Okay, so we need to put a little bit of context. So we interpret gravity, so Einstein, and also we, together with Einstein, interpret the gravity as the physical manifestation of the curvature of the geometry of space-time. So basically, we want to associate the part that is the geometrical part of the space-time with the matter-energy distribution. And for doing this, we need the Einstein field equation, EFE, I don't know how to say it. So basically, on the left, you have the Einstein tensor, which is basically a coupling of this Ricci curvature tensor and the space-time metric tensor. And on the right, so on the left geometry, on the right, you have matter with the stress energy tensor of matter fields. So basically, this is quantifying how the energy density is leading to curvature on one side, and on the other side, how curvature is influencing the energy density. Okay, there are 10 coupled nonlinear partial differential equations. So this is basically a nightmare. I still remember in my university years to do this kind of mathematics. There is also the lambda, you know, remember the vacuum energy, the lambda factor. Now let's not discuss also this, but I just wanted to mention it for clarity, that there is also the discussion about the lambda term. Okay, so basically what is happening? So if you want, so the generation of the gravitational waves is implicit in the solution of the field equation. You basically need to do, like let me say, we mostly do in physics, a lot of approximations. So you can start with an approximation, and basically what you can do is to start, consider a small and flat region far away from a possible emitting, so non-static source, like for example, two massive objects that are orbiting next to the other, and then you find that the gravitational field should vary with time. So what do is you can take a small effect that is perturbing the Minkowski metric eta nu v by only a small account, and here you have the metric that we saw, the space-time metric before, that can be expressed like this. Okay, then if you want to use another type of, let's say, mathematical approach, you can define this with the Laplacian of h nu minus 1/2 h eta. I mean, it's, as I told you, particularly complicated, but you can do it, and you can express the same equation that we saw before in this way, with the metric on the left and the matter on the right, where you can express this. I believe most of you more or less saw already this. Okay, what is happening if you consider the solutions in vacuum? In vacuum, it means that what you have on the left, on the right, from, okay, depends on the point of view, you basically put it to 0. And so you find the solutions of this possibility. And what you find are these couple of 4 solutions with these 4 amplitudes that basically give you 2 possible, let's say, shapes, let me say, of your solution, of your gravitational waves, that are either cross solution or, so to say, plus solution, in which you have your oscillating wave that can be oscillating. Now I think, I don't remember if I have it. Yes, I have it here, so you can see it better. You have the cross solution that is oscillating in this way, and this is the plus solution. So you can imagine this as a wave that is propagating through the z-axis, which is the axis, let's say, towards the observer, and this is the mode of oscillation of your, let's say, of your gravitational wave. So this is somehow an optical visualization in order to understand what is the effect of the gravitational wave that is somehow impinging on these black dots that would be some free fall test masses of a possible detector on Earth. So this is a little bit what we expect. So you have this continuous deformation of the ring of these 2 ellipses in order to understand this. Okay, there is a lot of text here. I even don't remember exactly what I wrote in all of this. So the point is, now you have to understand what is the relation of this gravitational wave to the source that is producing it. And so basically, you have to study the situation where matter is non-zero, okay? And so you have to study the different conditions for these solutions. And so in the different conditions, you have to take into account all of the possible properties of your source, in particular, the scale dimension of the source, the time frequency of the variation. And then, obviously, this energy tensor, this T, is dominated by the rest mass of these possible objects that you are considering. Then you have to make a lot of approximations, as usual. For example, that the wavelength that you are measuring is much bigger than the dimension of the emitting source of R. That the distance source approximation, so that you are looking at the gravitational wave from a much longer distance than, obviously, let's say, always the scale of the object. And doing everything, I mean, if you do all of the proper calculations and everything, so you can measure, you can find the final effect of the gravitational wave with this expression here, in which you have this Q, which is basically another term that is connected to the mass of your object. And what is interesting to see in this relation is that this, let's say, the effect of the gravitational wave, this age that you are measuring, is inversely proportional to the distance of the source, meaning that if you are measuring a gravitational wave that is more nearby, you will have somehow a stronger effect, let me say, than a gravitational wave that is more far away. So what are the classes of possible gravitational waves? So we have either transient or non-transient. This I didn't say this morning, in the sense that I made it a little bit, I mean, for me it was obvious, but I'm sorry. So obviously gamma ray bursts enter into the transient world, in the sense that it's a signal that is not a steady signal like a star that is always there and you see it all the time, or an AGN that is always there and you know. So a transient event is something that is happening and then you don't see it anymore. So it's transient in time, basically. So in the transient, on the transient part, we could have several, let's say, candidates, like, for example, as we already mentioned today for gamma ray bursts, the coalescence of compact binary system. For example, 2 neutron stars or 2 black holes, or 1 neutron star and 1 black hole, which is, by the way, spoiler, the only source that is detected so far. Or a core collapse of a massive star, or you could even have non-transient sources, like, for example, a single neutron star rotating and producing gravitational waves, or the gravitational waves produced by a stochastic background. They could be, let's say, unresolved sources or Big Bang relics. These transient events, like, for example, as I said, this compact, this coalescence, they would produce high frequency gravitational waves, these transient sources, that are the ones that we will see in a second. As I said, either neutron star or binary black holes. You can see here to get an idea of the energy that is emitted in terms here of solar masses. So this is now again another measure that you have to take into account. While let's say the predictions for the core collapse of the massive stars, so these are the so-called unmodeled, so these are the modeled sources, these are the so-called unmodeled sources, but you see already here that the energies emitted are much, much, much smaller than the ones that are produced in the coalescence of 2 compact objects. So this already pinpoints to something that is more different. I have one numerical example, I think in the next slide, in which you have just to understand how you put all of your, I said you need to have the parameters of your source in order to understand how strong is the signal that you expect to measure. And so you can create your model with your two bodies, so we have one with one mass and one with another mass that they are orbiting in close binary orbit. You can obviously using, for example, the third Kepler's law, putting together the angular velocity together with the size and the total mass of the system. And you can take again, there is a square? Oh, here. Okay, sorry. Yes, I will. Thank you. I will correct the slide before uploading it. So basically, it is possible to derive the to derive the order of magnitude of the signal of the gravitational wave, which you see depends, okay, in different, it's always the same formula in different versions, so to say, but you see depends really on the properties of your system. And this is basically what is happening nowadays, vice versa. So you have your model with this, you find a gravitational wave, and based on what you measure, you are able to reconstruct, going backwards, the original parameters of your source. And here you have an example. So if you consider two bodies, for example, with a mass of the order of 1.5 solar masses, with a Schwarzschild radius of about 4 kilometers, merging when they are 100 kilometers apart at a distance of, for example, 40 megaparsecs, you have this parameter, this age, the strain, the order of magnitude, is of the order of 10 to the minus 22, which is very small. So this already tells you that it is a complicated history. So we are going towards a complicated history. So to give you, to get a feeling of the effect, it's that the distance of the Earth from the Sun is changed by the distance of one atom during the passage of the gravitational wave. So it's really here lies the challenge. It is 10 to the minus 22, okay? This is the challenge of being able to measure changes in distance of the order of 1,000th of the diameter of a proton. So it's really, really, really challenging. Okay, so I mentioned this distance of the merging objects. So basically you have that this range of frequency is the one that is particularly relevant, but it is not, because sometimes I also get this question, so can we hear, because we will see it in a second, many times it is very useful to model or somehow to reproduce the passage of the gravitational wave with a sound. But it's not possible to listen to the sound really of a gravitational wave passing by, because the frequency is different than what is, let's say, audible by human frequencies, because this is also something that people, so the GVs cannot be detected by acoustic devices. Okay, so we have this GV that is propagating at light speed. And we want, so this age, this strain is the distortion of the metric. But how do we translate this distortion of the metric into something measurable? So we need to have something that has a particular distance. Now we will see what it is. And this distance will be varied by the passage of the gravitational wave. And so this delta, this variation over the length, is basically our strength, and so we can go back and calculate how much, so how big has to be this difference in distance in order to catch the strain. It's of the order of 10 to the minus 18 meters. So technologically, we need to arrive to this precision in order to be able to measure something like this, okay? So the point is, another thing is sometimes I am also asked, so but is it more or less as difficult as neutrinos? Well, actually, gravitational radiation is suffering even less absorption than neutrinos when passing through ordinary matter, so it's even less absorbed than neutrinos, and somehow, let me say, it's also even more difficult to catch than neutrinos. By the way, it is also impossible with the current technology, let's say, to produce, because this is another thing that one could say, could I produce a gravitational wave in the lab? So actually, this is not possible yet. And this is let's say, an image that shows how big is this 10 to the minus 18. So this is a proton, an hydrogen atom, and this is just to give you a feeling of how big this variation in length is that you need to measure. So 4 times 10 to the minus, okay, this is starting again. So it's really, really, really challenging. So how difficult was it to arrive to finally measure it? So I'm coming from the experiment, I'm an experimental physicist, so this is what amazes me the most, so how technologically you could build it. So the idea is that, so if the GVs are exerting tidal forces on some masses, the idea is that you need to have something that is somehow oscillating. And actually, at the beginning, there were the first experiments in the 60s. They were trying with some, let's say, with some prototypes, with bars, for example, with aluminum bars, to see if they could be made to oscillate. And actually, in 71, Weber claimed that with his instrument, with his resonating bars, he could measure gravitational waves from the direction of the galactic center. Boom, like this. Okay, actually, there were many, many other bar detectors that were constructed in the same periods, but nobody else was ever confirming this claim. So actually, the aluminum bars of 2 meters in length and 0.5 meters in diameter, they are somehow too small or inappropriate to have these. Okay, this I already said. Let me say, okay, so basically the big breakthrough towards, let's say, the 80s was the idea to start to build these so-called interferometers, but not like the bars of a few meters. As you see, like already here, we will see it even more in detail later on, you need to make something that is oscillating, that has a very, very big length. So this L, you need to work on the L somehow. And so you have the beginning of the idea of the so-called laser interferometers, and we will see it in a second, because we need to go to this order of magnitude of the strain that is of 10 to the minus 22. This is the position of the actual generation of gravitational wave detectors. We have both gravitational wave detector of the LIGO instruments in the US, in Livingston and in Hanford. They are both 4-kilometer long arms. We have the Virgo detector in Italy, which is a little bit smaller, 3 kilometers. We have the GEO 600 meters in the north of Germany. And we have the Kagra instrument in Japan. And there is the project of LIGO India that I am really not sure how the situation is right now with all of the fundings and everything. So I'm not part of the collaboration, so I really don't know how the standing is for LIGO India right now. So how did it go, let's say, technologically? So while Weber was doing his resonant bars, we had these two guys here, Rainer Weiss and Kip Thorne. So this is part of, it's not, I didn't put up the video, but this is part of a very nice video that if you want to have a look at on YouTube, it's basically also, if you go from the LIGO page, you can find it, that tells you the story of how to build, or how to succeed in building a detector that finally let's say, makes a breakthrough. And basically, you need to put together a very good theoretician and a very good experimentalist. So maybe most of you, well, you know them both probably because they won also the Nobel Prize for all of this. And so this is one of these reports that was written by Rainer Weiss in '72 with the first idea of this electromagnetic coupled broadband gravitational antenna, he was calling it, which actually, as the first reference, obviously was one of Einstein's papers. Okay, and here is the first sketch of the first idea of this antenna, in which you have basically a laser, two arms, and this splitter here. We will see it then much better in some animations later on. So as I said, it started really early, but it took a lot of time. So there was a first prototype at Caltech in the early 80s, 40 meters, not enough. And then in the 90s, they got finally the funding, because the problem is always money, unfortunately. Also, what you probably all know, also in physics, if you have the money, you can build wonderful instruments and do wonderful discoveries. So finally, they got approved in '95 to start the construction of LIGO in the US, and in '96 of Virgo in Italy. So in '99, the LIGO detector was, let's say, inaugurated in the US. This was it took a little longer in Italy because it was only inaugurated in 2003. So it's a little longer. And this is something that always amazes me, because this is a time in which I already was doing physics, doing my PhD, and I never heard about any, I don't know, I want to say any discovery, but when you then hear about the discovery itself, you think, but what did they do, all of these people, before the discovery? So was it just a discovery the first day that they opened up the instruments? No. Actually, they were taking data for, let's say, 10 years, not 10 years, but a little bit less. But there was a very long period in the years 2000, and a quite long period also for the Virgo instrument, in which the instruments were absolutely operative, taking data, doing their best. And as Rainer Weiss said, in all those years, we saw nothing. But they really, really did a lot of work. I have more slides after, yes, absolutely. So what happened then? There was a period in which, like it will happen at the end of this year, in which these instruments close down and do upgrades. They do a lot of upgrades on a lot of systems. And in all of this time, they upgraded LIGO to advanced LIGO and Virgo to advanced, this is Livingstone, okay, and this is Virgo to advanced LIGO. Okay, so the point is that LIGO was again ready 2 years before the Virgo. Virgo was ready because Virgo had lots of problems with some mirrors. So Virgo was 2 years later with respect to LIGO. So this is a sketch of how the interferometers are basically working, but I have also a video in which we will see so you have basically that the laser that is not a very simple laser, a very special laser that is split on a beam splitter, and then the two beams are going through the two tunnels of 4 kilometers, what it is. At the end of the tunnel, they are reflected by a mirror, and they go back. And either so now in this video, they are again, so to say, recombining, and their pattern of a recombined pattern is then projected on another, say, image, on the final image, the interferometric image, totally on the right. So now this is, so to say, the simplest version of it, in which you have a laser pump going back and forth, recombining, and if one of the two are, let's say, arms are changing the length, in the sense the length between the beam splitter and the mirror, then you have a different image at the end, and if you have a different image, it means that you have an effect of a passing gravitational wave. So actually, the history, I don't know if this video is working. Let me try to see. It's an online video. Okay. Actually, this is a quite long video. I don't want to show it all. But in the video, this is a video from the Virgo collaboration, it tells you a little bit more about the whole story, because it's not just one beam splitter, two mirrors, and an image at the end. So actually, what is happening is that the system is much, much, much more complex. Now here it is explaining the basics. So let me see if I can go a little bit further on. Because it's very long. Okay, so basically, what is the trick behind all of this? Because even if you go back and forth with your laser once, it's too short, it's not enough. So what you have is some other systems in the middle that make the laser beam go back and forth thousands of times. And then you have some power, I don't remember the name, I have it on the next slide, that are even making your laser stronger and stronger at every passage. And so basically you have a beam that is traveling thousands of kilometers, gaining power, recombining, and in this way, so in this complicated way, then in the end you have a final product in which it's a little bit easier to see this difference in distance. Okay, you see, so it's a very long video. I don't want to show it all, but it shows all of the details. Then another thing is that obviously there can be the Earth crust movements and all of the seismic noise, and so everything that is there, it's not on the ground, but is how do you say it? Suspended. Thank you very much. And so you see the complexity growing and growing, because the earlier video was really, so to say, an easy history, and this tells you what in reality you need to do. Then obviously everything needs to be in an extremely high vacuum, because you need to really put also the thermic noise to the minimum possible. So you see this animation, it's really very nicely made, this video, and it tells you what you see, the vacuum system that I was telling you, and it covers everything, and then you can do, okay, let's move on, otherwise we stay here all the day. Ah no, this is, now I need to, where is it? Perso il mouse. Okay. So basically, another thing that is very important is that in order to be, to validate somehow your signal, you don't need just one. Well, basically with one you can do something, but what we will see later on is that you have at least two, possibly even more detectors. You are able to locate your possible gravitational wave source much better, okay? So a coincident detection, at least with two interferometers, obviously is suppressing a lot of background. We will see it later on again. And it's improving incredibly the source localization. I will show you some maps in order to get you the idea of what it means just having one or two or three detectors helping up. So basically, as I said, the collaboration is a huge collaboration in the sense that it's not only LIGO or Virgo separately or CAGRA, but it's all part of a very huge network. And as I said, so the most important in the technology in order to be able to arrive to the detection are these these details, these things that I wrote here, like the laser, the seismic isolation, the vacuum system, the optical components, and also the infrastructure to be able to compute all of this. Okay, I don't want to go into the detail of the cavities, of how it is called, the power recycling mirrors. But as I said, you really need lots and lots of technology in order to make these things to work. And it's really complicated to find your signal because there is a lot of noise. And depending on the frequency, there are different types of noises. So for example, if you are at low frequency here, you have seismic noise, Newtonian noise. At high frequency, you have this shot noise, the thermal noise. There are lots of noises. It's an extremely complicated analysis. I don't know if some of you maybe work in LIGO and can say something about this, but in general, so this is not a simple science, so to say, not a simple data analysis. You say, okay, analyze just a second. It's really complicated. Okay, let me go back to what was happening before, because as I said, I was very curious. And I said, okay, but before 2015, nothing happens. It's not true, because there was a huge work prior to 2015, not only by the gravitational wave community, but together with the other, let's say, wavelength community. There was a huge working together in order to find possible counterparts to each other. So apart from the work on gravitational wave to see if there was some signal, there was also a huge follow-up by the gravitational wave detectors to see if there was some signal in the GV following the possible transients, gammas, gamma ray bursts, and everything. So these were the expected transients. Or some of these slides that I show here are from Marica Branchesi, who is an Italian professor in L'Aquila, who dedicated basically her life before the true detection of gravitational waves to this multi-messenger really effort in order to be prepared, because you cannot discover something if you are unprepared. So basically these I already said at the beginning, but I wanted to say again. So basically we wanted to see if with some of these coalescence we could try to find something, okay, or with the core collapse of massive binaries. And so the idea was all the time, not only, obviously, also detecting gravitational waves themselves, but also the true quest was to find gravitational waves together with an electromagnetic signal. This would be really the breakthrough that people were working so hard for so many years, So a coincident electromagnetic and GV signal together could potentially be used to, obviously, to understand better the cosmological distances, to understand what is happening in the central engines. I was talking the whole morning about central engines, so to understand if it is supernovae or GRBs powering possibly some gravitational waves or producing gravitational waves, to understand the evolution of massive stars, to understand more about neutron stars in general, so their equation of state, okay, and much more. But would be, what could be an electromagnetic signal produced by this merger? And it was a little bit at the beginning. So these are all, I want really to pinpoint to this, these are all slides, all slides in the sense these are by Marica, but this was a whole, how do you say, a whole science that was already very clear before any detection. So the idea is we want to, what could be the producing a gravitational wave and an electromagnetic signal? Well, basically, if it is a neutron star or a neutron star black hole, we expect this. We expect short gamma ray bursts. because of what we discussed this morning, because this is what we knew in those years. So we knew that short gamma ray bursts were the ones associated with coalescence. They were, well, I wrote short hard because we said they are a little bit more spectrally hard. They are also, this I didn't say this morning because I didn't have the time, like probably now, but nevertheless, so the short gamma ray bursts are sometimes seen, but not in coupled with supernova or hypernova that I was mentioning. They might be or are, for some cases, seen with much less energetic supernovae, and the less energetic supernovae are called kilonovae. So the idea is, if there is a gravitational wave, there could be a short GRB or a kilonova, but also vice versa. If I see a kilonova or a short GRB, maybe I can catch a gravitational wave. So it's, yes? The y-axis is the, I told it this morning, is the hardness ratio. So in a gamma ray burst, if you measure the energy of your event, you can divide your event in high energy and low energy photons. Then you build the ratio, and this is the hardness ratio. It means basically that short bursts have a little higher energy, are harder, and long bursts are softer. So this is the HR diagram for gamma ray bursts. And okay, so the other thing is maybe we can detect a gravitational wave connected with a collapsar. So it would be connected with a possibly long gamma ray burst and possibly with a supernova. Okay, these could be some associations. Could we expect electromagnetic counterparts from merging two black holes? So there was a lot of debates over the past 10 years about this. In principle, no. So the short answer would be no. Then the theoretician probably find the solution. But theoretically, a black hole shouldn't emit light. Okay, so when you have two black holes colliding, you should not see electromagnetic radiation coming out of it. It just would be a collision and staying silent, staying black, so to say, okay? I want to mention this because if you would find an electromagnetic counterpart to a merger of two black holes, that would be a surprising event. Why am I saying this? Because something like this actually happened at the beginning of the detection period, so I will skip this because it's too long. This is the explanation of what a kilonova is with some ideas of how big it is, how it works, but I will skip also this. Okay, this is some associations between kilonovae and short gamma ray bursts, just to give you an idea of what we said this morning. And these are all good, let's say, good candidates. So these were the rates expected for LIGO before 2015, so to say, in that period in which the detectors were shut off. You remember it was the big upgrade, okay? So these were some rates of finding neutron star, black hole, or black hole. So the idea is if there are neutron star, maybe we can also see some electromagnetic radiation for the black holes, which are the most abundant candidate for gravitational wave. Maybe we won't see any counterpart. So this is what, to answer to what was asked before, this is a little, I'm sorry that the, okay, the plot is, I'm sorry, the plot is, anyway, so this is what was happening with all of the data that was taken in the years 2000. So they knew about the gamma ray burst because there was all of the gamma ray bursts that were seen by Swift and by other instruments. So what do? They went in their data and they did GV searches. We call this kind of searches triggered. What does it mean? It means that you play dirty because you already know. Because you already know when to search. In principle, you also already know where to search, okay? So they took all of the data in, so if you have a known GRB event, time, and sky position, you go and you look if there is a GV event associated to that event. So here there is written that they were taking good data, and there is written that basically there was no detection, but just placing of upper limits, basically, okay? No evidence of gravitational wave counterpart. So this is really the GV community following up the electromagnetic community to see if there is something in that moment of time when you know there is a burst, if there is a gravitational wave event. Okay, so here there are some upper bounds, lower bounds. There were also, now I'm focusing, I am biased, I am focusing on gamma ray bursts, but there were other triggered GV searches. For example, for soft gamma repeaters or anomalous X-ray pulsars, there were many searches for cold collapsed supernovae. Well, there was a lot of work. So you see here all of the papers, if you are curious and you want to go and see. So there were many searches also in the other way around. So it's not only I'm waiting for a gravitational wave. It's I know lots of sources. I see if those sources are in my data. The photon energy? I don't think so. Well, I don't know. I don't think so, in the sense that, well, actually, what you know from the strain and what you know from your gravitational wave can be all of the parameters of your system, so the masses, the distance. In this sense, you can make probably, let's say, a guess of obviously what is the progenitor of your event. From the progenitor to know how strong the possible gamma ray burst is, I don't know. Probably there are models that tell you this. I'm not an expert about these models. I've never done anything like this. Probably there is, but I'm not really sure. Okay. Okay, these were searches for continuous GV signals. Okay, I don't want to go also because it's late. But in general, so you remember this morning when I told about the GCN and all of this information going around. So the idea is that you have to be connected to all the other communities to know if there is a GV trigger. If you have a sky position, you need to be as fast as possible in order to inform your colleagues, your other, or the other instruments, missions, whatever, that they can, so that they can follow up. And so there was a tremendous amount of work in order to have these latencies as lower as possible. These, again, these are all older slides. So this is telling you that you see the latency from when you have the trigger to when you are out in the world is like 30 minutes. It's a lot. Because if you think about what we saw this morning, GRBs, they are fast, they fade away. 30 minutes in GRB time is too much. Okay, so you need to work on the software side, on the communication side, to get this faster as possible, to get it out. And this was the creation, so to say, of a huge network. You see how many instruments, how many other instruments were also building networks in the sense what we call, so they were signing the so-called memorandum of understanding, which means you collaborate with another instrument even for data which is maybe not public. Okay, so you have a preferential channel of information and you pass your information to other instruments in order to be as fast as possible, and you have to have all of these networks. Okay, let's skip this. These are the follow-up, and here it is. So this is the situation in February 2015. So there were 60 of this memorandum of understanding with different countries, with different instruments, with all the wavelength, because everyone wanted to follow up as much as possible gravitational waves events. So unfortunately, the video does not have, okay, I'm sorry, the video doesn't have audio, but anyway, so this was the very famous press conference in 2016. I remember I was skiing that day. It was a skiing weekend, and there was, yes, and this was, okay, it was in the morning in the US, and I was watching the video in the evening in Italy, and I remember, and the guy is saying, okay, we detected gravitational waves, we did it, and everyone is cheering. And every time I listen to this, I remember that day, I really had goosebumps, because it was, I mean, after so many years, it was really an emotional moment, I have to say. This is the paper of the detection. And they put it on the physical review letters. So it is, so for Einstein, they put it on the physical review letters, okay? So this was the observation of the gravitational waves from a binary black hole merger with particular properties. Here are all the properties. The initial black hole mass is 3629, the redshift, because of this distance, 400 megaparsec. I think I have some more, okay, here. I don't want really to go so much into the detail, because I also wanted to talk a little about Fermi, but so this is the first event that had a combined signal-to-noise relation of 24, seen by both Hanford and Livingston. And here you see the signal of the wave that is getting stronger and stronger before you have the final moment in which you have the maximum of the frequency, and then it fades away. I'm sorry, because I have also, yes, I have also the audio here, which is like, something like this, okay? In which you have you listen, well, you see, but you also listen to the gravitational wave signal in the two detectors at the same time. Well, actually, after the, and here there is a little bit of explanation of what is happening. Basically, inside this signal, you have the coalescence of these two black holes. Over 0.2 seconds, sorry, the signal is increasing in frequency and amplitude in about 8 cycles, from 35 to 150 hertz in these 0.2 seconds, basically. And it reaches an optical frequency of 75 hertz. The object must have been very close, so they were orbiting around each other at 350 kilometers. And so this is the, you see, you can follow, basically, the in spiral, the merger, and then you hand the ring down, in which, basically, you just have the newly formed final black hole, and you don't listen anything else. And the system is gone, so to say. Here there is a discussion of the noise. Because, so, if you have one of these papers in which you describe the discovery of something for the first time, you need to prove that it's not noise. And so there is a huge part in that paper that is exactly convincing the reader, because you need to convince the rest of the world that your analysis is proved. I mean, it's strong. And so there is a very big discussion in order to try to convince everyone that how the noise treatment, I told you, is really a complicated analysis. And so you have, okay, here are the parameters of the first detection. You see the initial, okay. You can see all of the details later on. And this is the part I want to focus on. So this, at the time, was the biggest follow-up in history at that moment. So that day, you see, you had a lot of different instruments that they are all written here that tried in some moment, not only at the time of, obviously, of the wave, because this is, but for days, for weeks, they were monitoring. What were they monitoring? Hey, where are you pointing? They were pointing everything included in these both two regions. It's called banana-shaped region. It's really called like this. You see all of these squares. They were all the targets that the follow-up instruments made of this object to see if there was a GRB, a supernova, a kilonova, some electromagnetic signal. It was the first huge follow-up, this by 25 teams. It was really a milestone because really it was the first broadband campaign, and it was also so proving that the community is able to do this kind of follow-ups. That can also be, so everything I'm telling you today can also be translated, for example, to neutrino physics, because when you have an ice cube golden alert, now it's more or less the same if you have a good, so everyone is looking, everyone is following. But this in 2015 was really the first time in which there was this huge, no coincident triggers from space-based observatories. It means that no satellite did automatically trigger, However, GBM, which had one of these MOUs with this agreement of data sharing, started to do some so-called offline searches in which you take your data and you do thorough analyses that are a little bit better than the analysis that are done by the flight software, in which you just, you have the trigger events and the GRB needs to be strong, well, not super strong, but it needs to be a little bit stronger. So here is an example. So the ideal case is when the GBM signal and the LIGO signal are both strong. But you can even have the LIGO signal and a very weak GBM signal, or you could have a strong GBM burst and not so much in LIGO, and then there is the worst case scenario in which you have not so much. So starting from this, there was a huge effort in GBM to have these offline searches moving on already from the year before, from 2014, but also in 2015. And so there are two types of searches that we do with GBM. One is the so-called untargeted. So you basically take all your data and you analyze them, you put them into a pipeline that constantly is looking for sub-threshold events. So sub-threshold with respect to the trigger algorithm that you have on board. And with these sub-threshold events, actually, we are gathering every year more events and more short events than the ones that are usually triggered by the instrument. Moreover, there are also the targeted searches, and this is playing dirty in the sense that you know when it's happening, so you know the time. So when you know the time, you open a window and you can play. I open a window of 1 second, 2 seconds, 3 seconds, how much you want, but you specifically have your pipeline working there and then, because you know there is a GV signal. So everything was prepared and tested on some Swift GRBs, and this is what happened in 2015, that we, the Fermi GBM team, we claimed to see some signal. This was a GCN, the GCN that we wrote. With this sub-threshold targeted follow-up, we identified the possible transient beginning 0.5 seconds after the report LIGO burst. So this was a little bit of a nightmare because, as I said, it was a black hole. The whole community was not expecting something, so basically everyone was getting crazy. Ah, GBM saw something, it's impossible. So it was tough times. I don't have a very strong personal opinion about this. So I don't want to say I'm absolutely pro this association or against this association. I am part of the team, so let's say I am more, somehow a little bit more possibilistic, so to say, about this. Also because it's 10 years ago, now I will show you what happened in the meantime. But at the time, we had lots and lots and lots of criticism from the community. So I remember some conferences in which the audience was really against us, like in a very, very tough way. So why? Because this is the signal. Okay. It's very, very low. This false alarm rate is very, very low. And the sigma, you remember this morning I said the famous 5 sigma, we are at 2.9. Okay, it could be something more backgroundish than, okay. It's the one that I showed you before, the banana. The big, I show you in the next slide. Sorry, here it is. Okay, so the localization was unfortunately underneath the Fermi spacecraft. So it was hitting the detector somehow from the side below, which is bad. Okay, the point is that even if our localization was very bad, if you put together the LIGO shape together with the GBM, even if it is bad, you can find a LIGO plus GBM region that is obviously smaller. So this thing here now, apart from is the association yes or no, is proving that if you have another instrument that can help you with the localization, you can shrink these regions of the produced by the gravitational by the interferometers, which are relatively huge, to a much smaller location, and this would be very much better for example, for ground-based robotic telescope, because with the ground-based, also this thing here is, I mean, it's enormous, okay? So there was an analysis of this short burst. Basically, it could not even be fit with a band model. This is just a power law. Okay, so with a very low fluence, so it's a very, very weak event, if it is an event at all, okay? But we learned, okay, sorry. So these are the evidences for and against. There is this 3 sigma false alarm probability. The region is more or less coincident. And we also did the cross-check that it could not be, for example, a soft gamma repeater or a TGF or another of the classical GBM sources that can be seen. However, the significance is very low, and this is what was not convincing the community at all. Lack of corroboration by other experiments. And this is what changed the game then 2 years after with the other event. So the fact that SWIFT, or the other instrument that was orbiting at the time that was integral, did not see the burst, was the strongest argument against this event. Because if nobody else is seeing this GRB, probably it's not a GRB. So it was very difficult to convince the community. Plus, let's not forget theory. It's a black hole. We should not be seeing any electromagnetic counterpart. It was not. So it's more, well, it's not completely from the Earth, but it was on probably on what we call the limb of the atmosphere, yes. It can be, yes, the atmospheric. It's one of the possibilities, yes. Actually, if you look at the spectrum, also the limb can be fitted with this kind of power law. We had a lot of discussions in these years, yes. But the point is that afterwards, that I will show you in a minute, we reanalyzed after 01, after 02, after 03, all of our data with the same technique, and this is still the only event that has such a high false alarm, well, the 3 sigma of the whole 01, 02, 03 of all of them. And it's 0.4 seconds in time with respect to its chance, okay. But even after, so this was a huge debate at the time. But as I said, even after so many years, it remains an event that if we run all of our pipelines, we don't pick any other of these ones. It's just that one. So if it would be simply background, how many background events do we have? A lot, because it's an inorganic scintillator that is triggering all the time with lots of particle events. And again, you see, it's very interesting. It's a very interesting case. Let's say it like this. Okay, so this was the end. What time is it? It's very late. Okay, so the first, these are some results of the first observing run 01. There were basically just these 3 guys here, the one that I show you, plus these other 2. These are the localization errors that are pretty huge of these events, and these are the masses of the events with all of the properties. No other detections were done for GBM for the other events, and also not from the Large Area Telescope. I don't remember if I have the slide here. Yes. So I will not talk anymore, let's say, more in detail about the Fermi-LAT, but you just need to know that in Fermi-LAT we already developed 10 years ago, and it's running right now, very detailed and dedicated pipelines in order to look for possible GV counterparts. We don't have any results, but we are constantly publishing our upper limits in an online catalog. We also used to publish our upper limits in the GCNs back in 01 and 02. Now in 03 and 04 there are so many events that we stopped publishing the upper limits because we just have online tables with the results, but there was no GV, MEV emission ever detected by LAT. Computation of upper limits, and that's it. Okay, so these were 01 and 02. You see, 02 started at the beginning of 2017, and this was the first event that was seen by 3 detectors. So the 2 LIGO and the Virgo 1, and it happened on the 14th of August. So again, beach time, because it was the 14th. So this was the first. And this is to get you an idea of how much better the localization error is when you have 3 detectors. So you see how you shrink the localization error brutally. So you get down with LIGO, so with Livingston, Hanford, and Virgo, you go down to 6. It's a lot, 60 square degrees. You cannot point VLT, okay, but nevertheless, it's much less than the other ones. This is the signal. Okay, in Virgo, it's not very prominent, but there is also the signal in Virgo. And you have all of, okay, you always have the references in all of the slides. This was, again, a black hole coalescence. Okay, here you have also an animation of, there are very nice, so actually this is not an animation, this is really a computational simulation, so there is a lot of mathematics in this simulation here by the Max Planck Institute for Gravitational Physics. But 2017 was, in the end, famous for the gravitational waves. And these guys here, they got the Nobel Prize for, let's say, after the 2015. Why? Because for the Nobel Prize of 2016, they announced it in February. It was too late for the nominations for the Nobel Prize, so they got it the year after, in 2017. So not only the theoreticians, but also the experimentals, also Rainer Weiss. So they divided, so to say, the prize among, and also with Barry Barish. So, but there was another breakthrough from my point of view in 2017. There was another press conference. This press conference was in October of 2016. And the person that had the honor to open the press conference was a colleague of mine, Julie McHenry, who was at the time the analysis coordinator of Fermi-LAT, of the Fermi mission in general, not Fermi-LAT, sorry, for the Fermi mission. And she said the gamma rays, the highest energy form of light, kicked off the light show. So what does it mean? That we have a gravitational wave, but it all started with a trigger from somehow from GBM, at least from the public side. Then now I will show you a little bit. So I will tell you the story chronologically. Someone before in the break was asking me what is T0. T0 of gamma ray burst is always when the first instrument detects the gamma ray, obviously. So it can be the Fermi GBM, it can be Swift-Batt, it can be integral, but it's the beginning of the burst in the moment in which the detector gets activated. So in the case of this event here, that happened 3 days after the Virgo one, because that was the 14th, now it's the 17th, and I was on the beach, yes. Yes. Unfortunately, okay, there was my colleague in Germany that took care of everything, so I was happy and I was relaxed, but okay, it would have been better if I was there. So there was the gravitational wave signal. So when you look at the history of the whole event now, after so many years, we put the time, the T0, let's say when LIGO and Virgo detected it, okay? But the point is that it was, as I said, it's not like a public announcement. So there is some delay in which the people in LIGO need to analyze the data, get the information out. So in the meantime, nobody knew. In the meantime, there was a GBM trigger. This time, a trigger. So this time, the instrument triggered alone, no targeted searching, nothing. It was a trigger, okay? So here you have it in different energy ranges, low energy, high energy, whatever. So again, here there is the audio, which is not there. You see, basically, you have first the gravitational wave, and then after 1 second and something, you have the GBM trigger. Actually, there was another instrument, it was the integral SPACS, that also triggered the GRB. So we were all very happy that they were all the same thing. Okay, you have more animations and media. Okay, so we had the first notice coming out after 16 seconds. This is automatic from the from the GBM instrument. Then you have all of the informations going out in the world, 27 seconds. An automated ground localization, 40 seconds. LIGO report on the GV trigger came after 40 minutes. And in the US, it was the chaos of the world. All of my Fermi colleagues were getting completely crazy, also because for Europe, it was during the day. But for the US, it was at the end of the night and the very, very, very early morning. So people were having breakfast and collapsing, basically, because there was a complete chaos. We had the first localization by GBM, by someone checking you see, wake up, because it was really, you see, this morning's GBM trigger has a friend. There were lots of emails going back and forth. Here you have, okay, again, the triangulation, because it was also seen by Virgo, and this was let's say, the banana shape of this event. Okay, then we did an extra report. There was the speed report after 77 minutes, blah, blah, blah. Then at some point, there was also neutrino. GV, neutrino, no, and then it was mistaken. Mistaken report. Because it would have been, someone again in the break asked me about neutrino, so this would have been like the event of all time, but no, there was no neutrino. Okay, here we had let's say, the map produced by the 3 interferometers. And then you have, okay, I didn't explain what is this IPN. So it's an interplanetary network that takes all of the satellite information, like SWIFT or Integral or GBM, and creates a co-localization that is obviously with more instruments, is more precise. And they were putting together it with the LIGO one, and you see this small region of, so it was shrinking and shrinking and shrinking the position. After 6 hours, already the position was shrinking a lot. After 6 hours, we were going towards the night in Europe and then also in the US. I mean, so you have to think about time passing. Why? Okay, then we had the GBN science circular. Here already there were some host galaxies that were found. And where is it? Okay, here you have another updated SkyMap, 11 hours, energetics. And here you have it. Here you have the breakthrough that came when it was night in Chile, obviously. Otherwise, you cannot operate the instruments. And basically, we had this optical, you see it here, counterpart, an optical transient. And the nice thing about this event, it is called in different ways. So it is called GV 170817 or GRB 170817, or it is called from the supernovae people SSS17A, or from the IAU designation AT2017, it's the same event, okay? Okay, we had also the potential host galaxy and the host redshift. So this came after more or less 12 hours. And, okay. Then in the X-ray and in the radio, it was seen much afterwards, because the afterglow really needed to expand and to become luminous. So the X-ray came after 9 days, the radio after 16 days. So here you have all of the, okay, so this paper is the hugest paper of all time. My name is twice on this paper, because, yes, because they did a mess, and my name is together with GBM, but also with the Fermi Lab team, so twice. I mean, okay. Nobody checked all of the names, but this is the multi-messenger observation. So this is, actually, it's a very short paper. It's like 15 pages of authors and 3 pages of paper, in which we, it's true, because basically we describe, I mean, this is amazing. We describe, here are all of the, so in the GV, in the time, you see the days, and then all of the instruments in the gamma ray, in the X-ray, in the UV, in the optical, infrared and radio, with the timestamp of when the observations were made. You see, so this is the LIGO-Virgo signal, Fermi GBM and integral, and then here you have, what is it, ESO and NT, so optical here. Here you have all of what you already saw before, and you have Chandra and the VLA in the radio. So it was, so this was even bigger follow-up, obviously, because this lasted for much, much longer. Actually, the paper was written really fast. This was amazing. So with respect to the 2015, that took much more cross-checks and discussions to publish, the first one. This one came out in October, so it was in August, September, October, 2 months. So it was extremely, extremely fast with a lot of people. And for example, Marika was also much involved in this paper, well, in the coordination, because you need to coordinate thousands of people with thousands of different communities, so it's really complicated. Okay, I don't really have time to go into the detail of the parameters. Here you have a very nice paper. This is the paper to which GBM, there were like 64 papers in the same issue of the Astrophysical Journal when this came out. This was the paper of the gravitational wave information together with the gamma ray information only. Then there were papers on every possible wavelength. But this is the one in which we really focused on gamma rays, okay? In which we discussed the time delay. So this is a very interesting thing. So the idea is that after the ring down, because you have this delay between the moment in which you have the merger, and then you have this time which is expected in order for the central engine to start and push out the jets of the GRB. So there is, if you are interested, there is a lot of discussion about this. There is a discussion about the spectrum. I don't want to go into the detail. Where it is as a temporal analysis, where it lies between long and short. This is, again, the hardness ratio. It lies here. Okay, it's very weak. It's a very, very weak event. It was also at a very low redshift, you saw from before. I will skip also this one. Okay, the nice, I will show you maybe later. Okay, these are some images about the afterglow. So these were all, again, Nature papers. Very important one in which you have the study of the afterglow. And I also have, okay, there was a very big study because actually it was a very low energy short burst. And also the properties of the emission that were seen in the afterglow. So it was interpreted as a very complicated structure in which you have some, how they are called, the cocoon. So basically there is a jet, but there is also a cocoon of material around. Plus there are some viewing angles, complications in the sense that we did not see probably the burst face on, but we saw, you see the eye of the observer, we saw it from the center of the cocoon, not of the jet itself. Okay, there is a vast literature about this. Again, I will leave, and also from the radio part, there was a very important study about this. I don't want to go into the detail. I just wanted to show you one of the last, I would say, papers that there were after how many years? So 2017, after 5 years. And this was a study of the peak was after 16 days, and this was the time since the merger. So this is 1,200 days. So how many years? They were following up this afterglow, this kilonova that was exploding together with this event. So it was really amazing. Okay, all the optical light curves. There is this wonderful animation that was done by the group of Elena Pian, studying the properties of the kilonova, the decay, and also another thing that could be done with this kilonova information was to study the production of chemical elements that you can do usually when you do supernova studies. And in this case, this is the table of the chemical elements that was revised, so to say, after this event, because you prove, so with the lines that you measure in this afterglow, you proved that you can produce particular elements. In particular, you see from merging neutron star, you can produce these kind of elements. And I remember that since this was so important, somehow we tried also to, I think, not only in Italy, but I think in every country that was involved somehow scientifically in this kind of event, you know, to sell it to the journals, but to the newspapers, the usual ones. So they need some catchy titles. And so at the time that they said, we found gold in the stars, because there is also the gold line, obviously, in this kind of. But newspapers need to sell, and so the gravitational wave, we find gold in the stars. I am rich because I found gold in the stars. Okay, wonderful. Okay, so what is the story so far? So these are a couple of slides that I borrowed from my colleague Max Razzano, who is part again also on the Virgo team. So there were many runs since then, O1, O2, O3 in 2019, O3b. Then, unfortunately, there was COVID, so everything needed to shut down. And now we are in O4. So O4 started in 2023. There were some breaks here and there. The last break was last year, and now we are ongoing somehow, apart from a small break that we had now in April. We are going probably towards the end of November. Here is the revised calendar, so we are more or less here, somewhere here, with the two instruments here. But we have also the Kagra, the Japanese Kagra, also entering in the game since this O3. What we have, there are catalogs now. So we have so many events that there are catalogs. This was the first catalog published in 2018 with 11 events. There are very nice animations of the mergers of these events. I mean, at the beginning there was a lot. Since there were few, there were many of these examples. Now that they have many more, there are less. Okay, this is one by one. Or the explanation of all of the events. Here is another beautiful image of the first catalog. Then the second catalog came out in what is it? Sorry, I didn't write it down. In 2021, okay, with 39 candidate GV events, so O1 plus O2 plus O3A. There are some cases. So someone already asked me in the break before lunch. So how many more of these events? Actually, there were not so many binary neutron stars. Mostly they were binary black holes already in these first catalogs. I highlighted here the second one, which is 190425. Then there is another which could be neutron star black hole or binary black hole. There is another one that is this asymmetric one. So there were many events. I don't want to go here. I wrote down every peculiarity of each event that we cannot discuss now. So why did we not detect another electromagnetic counterpart for this one in April? So basically, this is the error region. It was extremely poorly localized by the gravitational wave interferometers, and there was no coincident trigger in the, and also no subthreshold, nothing. So it was not seen by anyone else. Then there was another revision of the catalog called the 2.1. Here are some of the highlights. Again, I don't want to go into the detail. There is another nice animation that shows the couple of the masses of the two merging black holes producing the final masses of black holes that we know in our galaxy. So this is for the third catalog. So these are the 90 GeV. So you see every time in every observing run we have more and more and more events. These again are some highlights. I don't want again to comment in the sense that we don't have any other 1708, 17A. Unfortunately, until now we are still waiting. This is the page where you can find the updated capability of all of the instruments, and you see there is the prospect also for LIGO India for, let's say, next year. I don't know the dates, I don't know the details about this, but right now we are operating with the three, LIGO, Virgo, and Kagra. I don't really know, maybe our colleague here knows, if, because I was hearing about a rumor now with the Trump administration to have one of the two LIGO shut down. We don't know. We are in the hands of God. We don't know. We hope not. So everyone is praying not to, but yes, also we in Fermi are not that, so to say, calm about the situation, because we could also be shut down basically by the next year. It's true. We hope not, but obviously. No, this was not a pre-COVID thing. Okay, I think I already said this. So these were the follow-up programs. I don't want. Okay, so here are some of the upgrade. Oh, sorry. Some of the so this is the number of detections basically that. So there were a lot of upgrades over all these years in all of the periods in which the detectors were shut off. And so between O3 and O4, really you notice an increase in the detection rate. So in O4 we have already many more. You see O4A 81, 105, in total 290. So right now we have really many detection. And it's getting also complicated to follow up, because it's so many events that now you need to decide which ones you want to follow up or not. Obviously, if it is a candidate binary neutron star, everyone follows it. The binary black holes one gets less interest from the community. This is also the Newton cycle of the interferometers for O4A, O4B, and O4C. You see for the tripole interferometer, no need, okay. So far, the situation is like this. There is, okay, we have 200 gravitational waves right now. We have, you see, there are also these events that are the so-called low significance event that we also get in GBM. So my mobile phone all the time is getting, is exploding because we are getting also the low significance alerts. But this you can choose if you want to or not, if you want to be informed about the low significance event. Okay, these are the last highlights that were shown. This is an event that was, I think, shown in, no, not this one, sorry, this one. This was the last one that was announced recently about this event, is 231123, that is the heaviest black hole that was seen. I think this is all I had. Let me see. Okay, here I had the ones for LIGO India, but this is a little bit, this is old, sorry, this is an older slide. This I already showed you, so this is again, or maybe this is the last one. I think I had another, sorry, I had I had a wrong, a wrong slide before, so this should be the most updated one, because this goes down up to, yes, to 05 to 2031. But as I said, we don't really know now with the current funding situation what to expect. So let's cross fingers and hope that we can do much more science in the future. Okay, I think I will stop here. Thanks for following also this extremely long lecture.
Questions? I could have guessed.
No, just a comment about the coincident detection. So LIGO 2 is a system of automatic online alert.
Yes.
And within minutes, you get sky localization and distance localization, just that, not the masses. It didn't work for that case because there was
17.
a huge trigger on the Lewiston detector, as you show. In one of the plots, there is a huge trigger. So initially, automatically, that trigger was classified as a single detector trigger. So for single detector trigger, the pipeline is not triggered. It goes off. Of course, since there was the Fermi trigger, everybody immediately went
to do the analysis.
To the analysis, okay, why we had only one loud trigger, not a double trigger? And people realized that it was vetoed by that huge glitch. But the glitch was very narrow. It's less than a second wide, whereas the signal was over a minute wide. So it's not been too difficult to subtract it. At least to make a rough subtraction is not too difficult. So immediately within minutes, we did the subtraction and ran the analysis by hand, basically, and found that's why that delay of 40 minutes. That is not usual. For double trigger.
I know that now it's, now it's after 10 years. Now you are super fast. I know.
No, but even at that time, double trigger were announced in minutes. But not that one, because it was initially classified as a single trigger because of the huge glitch. And anyway, glitches happen one every few minutes. So for a signal which is over 1 minute long, it's very normal to have a glitch on it.
Thanks.
So
I
that's
didn't
why.
know.
But
Thank you.
That's why people at the time said, oh, Fermi scooped us. They announced it before the NAS. But
come on.
no, people in LIGO were worried that
they were worried. Okay.
that we didn't announce it first. But I mean, that's how it was.
Okay.
Another question?
It's more philosophical question. First, thank you for the talk. It's about the Nobel Prize. When it's a discovery from a big collaboration, like with a lot of people, how to choose who's gonna get the Nobel Prize?
Oh my God! Does someone know from a large collaboration? Well, in this case was because of, I think basically the theoretical point of view of who worked the most on the theory, and from the technological point of view, I think it was so to say, I don't know how to say, the PI or the highest responsible, not the spokesperson. I think in the case of that Nobel Prize was really who got the idea of building that system. Really, but this is also the case for other Nobel Prizes that I know, that I remember. They really go to the person who is the chief who had the idea, the initial idea. What is happening in the latest years is that sometimes, so more often, I would say, the prizes are split, because it's true that it's not one person that has the winning idea. So, for example, when there was the Nobel Prize of the center of the galaxy black hole that was given to Genzel and the Andrea Getz and the other people, because they were, let's say, they were completely independent groups, but they arrived at the same conclusion with different techniques, with different studies, but so they split somehow the honor. How it works, if it is really a big collaboration, or now I don't have any example that comes into my mind, but usually you should award the idea, not the.
Yes. Another question? You're a student, then you.
Thank you. Okay, this is, I think, a rather naive question because I don't know much, but I was wondering, how do you know so certainly that there were, for the first gravitational wave signal, that there were two black holes orbitating and they merged at like 350 kilometers? That's like too precise. especially after seeing that the localization is not precise at all. So
Well,
how do you know?
It's two different things, and it's all about the modeling that I showed at the very beginning. So you have a model, and you put into your parameters, and you study the frequency, you study the time, how long your signal is, and all of these inputs. Obviously, now I wrote 350, but I also had, so all of these numbers that I showed, now I cannot go, it's like 100 slides before, but it's also coming with big errors. Because obviously, if it is a model, it's this 350, now I don't know, but it was probably plus 20, minus 35, I don't know. So it's always is a very big range, because we know we are physicists, there are always errors that needs to be accounted for. But yes, so it's all about the parameters that you have to your model of the shape, the frequency of your gravitational wave. Then about the localization is something different. So it really depends on this. So if you have your instrument, your interferometer is in a particular place of the Earth, so you are sensitive to a particular region of the sky. If you have another instrument, you have another region of the sky, then you cross-check them, and you get the shape. So it's not related to the shape of the signal. It's more related to the direction of the signal. And if you have a triple one, then you can have even better. If you have 4 in the future, we hope it should be really able to have it smaller. And if you have another coincidence by another satellite or something, then you can shrink and shrink and shrink. And it's independent, so to say, on the signal, the shape of the error region.
Thank you.
Yeah, well, I'm not an expert on this thing, so some words are kind of vague to me. You talked about cocoons. What
Yes.
are those things?
What?
What is it?
So, well, I'm also not an expert of this. So it's so the idea, if I got it right, is that one thing is the jet, and the other thing is the other rest of the matter that is it explodes out of the primary explosion, like the supernova, so to say. So basically, the rest of the material that is traveling much slower than the ultra-relativistic jet, that is expanding also more, let me say, isotropically, but it's okay. So it's like a broader region emission, and this is how they interpret it, because in that case there was the kilonova, it was studied a lot and everything, so which is really rare for a gamma ray burst, because as I told you, there are not so many gamma ray bursts that have been seen in coincidence with supernovae, so it's not a very well-studied matter. And this was also something that, another argument that was used in order to explain why the GRB was so weak, also because it was seen through this cocoon and mostly from the side of the jet and not directly inside the jet. This is how we interpreted.
Good. So if there are no other questions, I guess we can thank Elisabetta.
Thank you, everyone. Thank you.
And before we go for coffee, I just wanted to make